Hey guys, I want to get back to making some videos, and I thought what better way to do that than to make one about something that I really enjoy, and that's finite element analysis. And I get the feeling that a lot of the viewers on this channel aren't aren't real engineers, and they may not know what that even is. And don't worry, I'll get into all that. But this video is just meant to be an extremely stripped down, like no fluff version of a college or even probably a graduate level course on the topic. So if you watch the full video and you still can't figure out all this stuff, then just one of us is really dumb. It's probably me. I'm not a good teacher, and I accept that. So I love finite elements because it's the perfect, pure amalgamation, fusion of simple mathematics, like numerical methods, material science, a little bit physics, and you can reduce a complicated system down to a mesh of much simpler elements. And then you can predict with very, very high accuracy, believe it or not, how these structures will deform and deflect under different load cases and boundary conditions. And you can evaluate the material conditions in each part to say, hey, is this element going to break under this loading? And if so, what changes can I make to prevent that? How does the geometry have to be modified? And a lot of the time when we, myself included, we hear finite elements, we think about these complicated, advanced, and very, very expensive, like tens of thousands of dollars, like software suites. But a lot of the time, the simple mechanics can be coded up in 100 lines of MATLAB code, and you can reuse that code literally forever. And I'll show an example of that kind of code at the end of the video. And we just can't let the simplicity of this get away from us. You don't need a trillion cubic elements, nonlinear analysis to model a bike frame or even like a wind turbine blade like I drew here on the right. And so by the end of the video, you'll be able to implement a full 3D frame, finite element analysis, and you'll be able to simulate anything you can imagine that consists of these slender members. And one last thing before I begin, and again, if you're already lost in the vocab, don't worry, I'm going to explain everything, legit from square one. But this video covers the basics of finite element analysis for one-dimensional frames, but ultimately implementation of a 2D shell element or a 3D brick element or whatever is basically identical. It's like 95% the same exact stuff. You may have a little bit different stiffness matrix, but it's ultimately exactly the same. So without further ado, the prereqs for this. You have to know some stuff already. You should know a little bit about linear algebra. Matrix inverses, matrix multiplication is very important. Row times column, know how that works very, very well. Simple derivatives, simple integrals. We're talking about polynomials and stuff, very easy stuff. Maybe there's a sign thrown in there. I don't remember. It's very, very basic stuff. Springs. You have to know Hooke's law for springs. This is F equals kx. It just relates the force and the displacement on a spring in a linear fashion. So a spring has like a material or maybe a geometric or both coefficient called the spring stiffness coefficient, this constant K. Let's say it was 100 pounds per inch. If you wanted to move the spring 5 inches, it would take you 500 pounds, right? That's all it is. Now you're an expert in springs. Congratulations. Coordinate systems. You should know kind of what 3D space looks like, right-hand rule, the axes, translations, rotations, even transformations. I'll talk about that a little bit in the video. You have to know basic, very, very basic statics. It's not even hard. Like you should be able to decipher what my free body diagram drawings are showing you, what that even is. You have to know what a force is, a moment, which is just a torque, right? That kind of stuff. And it would help you to know what these three things are: stress, strain, modulus, stuff like that. You don't have to know that already. Technically speaking, I'm going to explain that. I have a little bit of a slide on that. But if after I explain it, you still don't know really what those things are, you should look it up. Go to bing.com, type them in, figure it out. It's not really that hard, but I can't spend that much time. That's a course in itself. We know what these things are. So you have to kind of know that kind of beforehand. It's very simple though, really. So some vocab words. I'm going to use these every other breath. So this is, important to know what these things mean. A degree of freedom, a DOF, is a way in which something can move or be moved. So I have examples here from a theme park. A roller coaster is a 1 DOF system, 1 degree of freedom system. Why? Because I could tell where every car on that roller coaster is just by measuring its distance along the track. It's 100 meters along the track, 200 meters along the track. One variable is enough to tell me exactly where everything is, right? Now, at the teacup ride, what is that? That's the ride where you have those spinning cups on the spinning platform. There's 2 DOFs there, right? Because there's 2 ways for you to spin, so 2 DOFs. Bumper cars is interesting because you can drive forward and back, right? You can drive left and right, but you can also turn, right? Obviously, left and right, forward and back. So you can rotate around the vertical axis there. So there's actually 3 DOFs for bumper cars when you drive bumper cars on a plane like that. So yeah, very cool. Now, what is displacement? Displacement is how much something moves or rotates along a degree of freedom, or just in general, potentially. So here I drew a spring, very, very carefully, as you can tell. This spring stretches how much? It stretches u sub x in the x direction, u sub x. Very, very advanced stuff here, okay? So what is finite elements? It's just some terminology. Finite elements is a method of discretizing a system. You discretize it into finite elements. So you can do this for any kind of system. You use a bunch of different differential equations you can solve with finite elements. We're focusing on the structural ones, obviously. So we have these elements here that are one-dimensional, like linear elements, and they connect these nodes in blue. And on the nodes, we're applying forces. Those are called nodal forces. And we're trying to compute the nodal displacements, right? So we're going to apply boundary conditions, we're going to apply forces, and we're basically going to assemble this kind of a set of equations, right? So you have a nodal force vector with all the nodal forces, even all the 0 ones. Let's say you're not applying a force here. Well, you put a 0 for that, right? You say you're not applying a force here. Well, you put a 0 for that. So this is nodal forces, and it's being related to nodal displacements. That's how much the node moves. Does the node move this way? Does the node move this way? Does it rotate around this axis? All that stuff. That's a displacement, right? And the way in which it relates is by this stiffness matrix K. K is the entire point of this video. We're going to spend the bulk of this video just figuring out how we can, model this system with, a very accurate stiffness matrix K. And if you remember, from kind of just above, I talked about, F equals Kx for springs. This is the same thing. F equals Ku, but ultimately U and X is the same thing. They're just displacement of a spring. Here it's displacement of a node. So this is very simple to springs. That's why I brought it up. Now, what is a 3D frame element? A frame element, we actually call this in aerospace, we call it a beam element all the time. I don't know why. But in reality, it's the frame element. It's an element that has every single degree of freedom being measured and kept track of at all the nodes. So the element has 2 nodes, right? And at each node, you can move in the x direction, move in the y direction, move in the z direction, unless otherwise constrained. And you can rotate about the x-axis, about the y-axis, and about the z-axis. So there is 6 degrees of freedom per node. There's 2 nodes per element, therefore we're at 12 degrees of freedom per element. Simple stuff. Now, here's the constitutive law that I had, just to refresh what stress, strain, modulus, all that are. So on the left, you can begin with Hooke's law. So Hooke's law was what I said was what relates to force and displacement on a spring, and that's what it is. Let's say K was 100 pounds per inch. You wanted to move this a foot, you'd have to have 1,200 pounds, right? That's what this linear thing is, and that's all constitutive laws are. They're just a linear relationship, in our case, that helps us relate quantities of interest to compute things that we think are important as engineers. So stress, what is stress? Stress is a force over an area. It's a kind of way to not really non-dimensionalize a force, but to generalize a force to a cross-section. So it's a normal force. That's a force perpendicular to an area here. Simple stuff. It's a pressure, basically, like PSI or pascals. That's what that is. What is strain? Strain is a change in length over a full length. It's actually the derivative, right? But ultimately, if you have a linear section like this, it's just how much longer it's getting over the original length. So if the original length was 1 meter and you stretched it, 2 centimeters, that would be a 2% strain. And usually it's measured as a percent, but also you can measure it in like microstrain or those kind of things. No worries on that. So just like F and X can be related by the spring constant K, you can also relate stress and strain by the modulus E. It's called an elastic modulus, and it's exactly the same format as this. You can see we have this is the the dimensionalized force thing. This is like kind of the normalized dimensionalized strain thing, and this is sort of material geometrically normalized stiffness thing. So that's all what that is. Yeah, this is just a material value. So these things have all the geometric data encoded into them, right? This is per area, this is per length. E is a material constant. So for example, aluminum has a modulus of 70 gigapascals, give or take, and let's say it yields at 0.2% strain. You can plug in those numbers, right? So 0.2% strain is the green one, 70 gigs is the blue one. You can compute the yield stress as just, modulus times the strain, 140 megapascals. Right, simple stuff. Now torsion is a bit different, not much, but a little bit different, and I would say a little bit harder. So in this case, we're not measuring things along the axis like a normal force, normal displacement. We're actually measuring like a tangential force and tangential displacement, a shear, basically. So in the case of the stress, again, it's a tangential force over an area, but it's still the same thing. It's a pressure, it's pascals or psi, and shear strain, that's just basically delta S over L. How much we're moving, in the opposite direction. Not along that length axis, but sort of, normal to that axis. And so, in the case of numbers like this, where like they're round or whatever, you can just equate this as the angle times the radius, right? This S, this sector length, is just the angle times the radius, right, at that location, and then we divide it by L to normalize this in terms of length. So the max shear strain would just be theta, that's the rotation that you're applying, times the full radius R, the maximum radius R, over the length of the member L. So just like F and X are related by K for springs, shear stress and shear strain are related by the shear modulus G. Same as above. And the thing is, you can actually plug in numbers here and do like a moment equilibrium. I'll do that right now just to explain this. So basically, if you apply a torque on this member about its central axis, you can take this, basically, what are the internal forces, internal stresses? They have to be equal to each other, and they have to also equal the applied moment. And so you kind of look at this sort of free body diagram here. It's very complicated, but ultimately you can plug in stuff, move things around. You can pull out this geometric quantity here. This is the polar moment of inertia, J. We will use that in the video. And also, the moment relates to the max shear force times J over R. You kind of plug in all these things, and you can evaluate this. For those that know structural engineering, this is already something that most people have memorized. Maybe they memorized this one. I don't really know. Maybe both. And so, yeah, actually, this, for those that know already, like this is already a stiffness matrix term, and we'll see that in the video that's going to appear. All right, that's the basics of, that's like the first 2 years engineering. Congratulations, you now mastered that. So FEA is just a bunch of springs. That's why I brought up springs, because it's entirely springs. So let's see, you had the system here on the left. You have 4 nodes 1, 2, 3, and 4, attached by springs 1, 2, and 3. Now nodes 1, 2, and 3 are fixed in space. That's what these hashes mean, but node 4 isn't, and so we're applying a force there with the X and a Y component. And in general, all the nodes here have X and Y degrees of freedom, but obviously 1, 2, and 3 are fixed in space, so those are all going to be 0. Whereas node 4, it has 2 true degrees of freedom. That's UX at node 4 and UY at node 4. So it can move in both those directions. It can move in this direction, basically. And by the way, this 4 is not an exponent. It's just talking about what node we're talking about. So you'll know the difference between an exponent and just a superscript here, it'll become very obvious. And also these springs have their own spring stiffness, obviously K1 for spring 1, K2 for spring 2, and K3 for spring 3. Okay, now if you look only at spring number 2, you cut off springs 1 and 3 right here, and you look at how this thing works. What do we know? We know that Fx, that's the horizontal component, does not stretch the spring, but Fy does. Fy is along the axis of the spring, and therefore it is stretching the spring. And so how much does it stretch? Well, based off of this Hooke's law, right? F in the y direction equals k for that spring times the displacement in that direction. And you can plug that into this matrix, equation here with the f's on the left, the u's on the right, and the matrix in the middle. And so this is the spring 2 element stiffness matrix. And you can see that rho times column, nothing to do with Fx. And then for Fy, only the Uy is multiplied by the constant, just as in the equation. Okay, simple stuff. Okay, now on spring 1 and spring 3, it's kind of the opposite, right? So for spring 1 and spring 3, those are the horizontal springs. Fy does not stretch either spring, right? But Fx does. So Fx compresses the left spring and it stretches the right spring a certain amount. How much? Well, by this equation and this equation, right? So the left spring is stretched per the spring stiffness constant, K1, and by this equation here. So why is there a negative sign? Well, it's because Fx is to the left, whereas we're measuring U4x to the right. Therefore, a positive force has to result in a negative displacement. Now, similarly, on the right-hand side, for this right spring, it's also negative because, again, a negative force in the x direction, a positive force is to the left, whereas we're measuring displacement here to the right, so negative sign. And you can plug this into the equation. Now, in this case, Fy, rho 2 times column 1, has nothing because there's no Fy in the equation, but Fx does have a value there. Long story short, you can take those terms and add them together. What does this mean? Well, this means that the force has to be distributed across all of the elements per their stiffness coefficients k, right? And so you can add these together, you can undistribute the degrees of freedom and pull out this matrix equation here. So 2 equations, 2 unknowns. In general, these 2 variables here, these are the unknowns. You'll usually know the forces because you're applying forces on the system and you're curious about how much it moves. So if you knew Fx and Fy, you could compute Ux and Uy, right? So all you have to do is take this equation, right, the original equation, and pre-multiply both sides by the inverse of k, and you get that the displacements is k inverse times f. Now, it's not always possible to invert this matrix because if you have, a 10 million degree of freedom system, this inverse operation will take a lot of operations, probably too many. So there are ways you could invert a matrix without taking its direct inverse, right? You can evaluate this in different ways with iteration, but we won't mention those in this video. We will have very small systems that we can evaluate just with the inverse. Okay, and all of finite elements is just an extension of that example, really. You may have more degrees of freedom per node. In that example, we only had 2 degrees of freedom per every node, x and y. Obviously, as I mentioned before, frame elements have 6 DOFs per node, right? But you can also have voltage and temperature and that kind of stuff too. So you can have many degrees of freedom here. Now, what are the different stiffnesses? So you may not always just have Ks for springs. You may have these material and geometric components to your stiffness. And we'll get into that in a second. You will also have different kinds of elements. You may not have just linear elements like lines. You may have shells and hexahedrons, tetrahedrons, that kind of stuff. That can all change. And you may have nonlinearity. So the astute among you may have noticed that, hey, well, Fx, it does actually stretch this spring. After you move the spring a little bit in the x direction, it's like this. And at that point, Fx is kind of pulling the spring more in this direction, right? As you go more and more to the left. And that's just a nonlinearity. So that's saying that, if we were to break up the force into pieces, so if it's a 100-pound force, we took it as in 10-pound increments, they would have incremental effects on the spring locations, in this node location. We could constantly be reevaluating these matrices with with sines and cosines and that kind of stuff. And we can reevaluate the nonlinearity, every iteration, right? That would be a geometric nonlinearity. There's also what we call material nonlinearities. That's if this constant is not actually constant. What if it varied as a function of the spring length? What if it wasn't a linear spring? What if it was, a different kind of spring? So yeah, that's all built in here. So all FEA is just a simple extension of this example. Really, it really is so simple to extend it. So what is a frame element? Now this is the bulk of the video. All like the front matter is gone. This is the actual meat of the video. So frame element has two nodes, node A and node B, and as I mentioned before, there's 6 degrees of freedom at each of the nodes. Now the x-axis is along the element, so from node A to node B, and obviously all the other, the y and the z-axis are just outwards, right? And obviously you have to, keep the right-hand rule satisfied, so x and y, cross those to get z. Besides that, it's whatever you want to define, you can define whatever way you want. And our objective in the video is to come up, at least right now, with a 12 by 12 stiffness matrix, because there's 12 degrees of freedom per element. We're trying to relate the 12 nodal forces in moments to the 12 nodal, displacements and rotations. Okay? And so let's say we were to fill out this row here. This row would just tell us how F in the y direction at node A is distributed across all of these degrees of freedom. You may have some zeros in here. In fact, you will have some zeros in here. And so we'll talk about how that all works in the coming slides. But that's all this is. Long story short, all we're doing is we're basically saying, how does this force distribute across these degrees of freedom? And how it does, we'll put numbers in this little box. And these numbers aren't going to be like 5 and 12. They're going to be geometric and material quantities that govern this relationship. And we're trying to derive what those proportionalities are. Okay? So the easiest one is axial stiffness. So axial stiffness is just the stiffness of the bar along its axis. So extension, right? And so we have node A and node B, and the x-axis goes from A to B. Length L for the bar, and we have a cross-sectional area A. So now again, we're measuring Fx and Ux at node A, to the right here, along the axis, and then FB goes outwards from the element. And so if we pull this modulus equation from before, equals stress over the strain, we can compute both stress and strain and plug and chug these numbers in and compute the stiffness terms. So what is the stress? The stress is just the force over the cross-sectional area. Now remember, statics, right? These forces have to be equal and opposite. If they're not equal and opposite, this bar is going to fly off into space. So FA in the x direction and B in the x direction, they have to be equal magnitude, opposite in sign. They have to be, it's a requirement. And so one of these has to be negative and one of these has to be positive, right? So the way we define this is that tension is a positive stress. That's the definition. You can change it if you'd like. And compression is a negative stress. So what does that mean? Well, that means, let's say you were to fix node A in space, hold it there still, and then pull node B with the force Fxb. That would cause this bar to get longer. That would be a tensile stress, right? It's tension. So positive sign on that one, right? And then if you were to fix node fix node B and apply a positive force, at A, that would be a compressive stress or negative. That's why there's a negative sign there. Now, what about the strain? So strain is just the change in length over the length. So that's just this quantity minus this quantity, right? So UBX minus UAX over the L. Simple enough. We plug in both these values here at node A and node B into this equation for the modulus. We can solve for the force. And in this way, we can basically pull out how this force distributes across these degrees of freedom. So if you can see, it's pretty much the same thing for both of them, just the sign is different. So a positive force at A causes a positive motion, right? This is a positive sign here at the UX at A, whereas a positive force at B causes a positive displacement at B. right, and negative at the other one. So as you can see, fx at A and at B are only related to ux at A and B and nothing else. There's no rotations, there's nothing in those z direction, nothing of that. All the other terms are 0. So we look at the matrix. This is how those two equations fit into the formulation, right? So you can see we have the first and the 7th rows, as well as the first and 7th columns. By the way, this is a symmetric system. So what's the first row? The first row tells us how force in the x direction at node A, that is, where is that? That's this one. How that relates to, well, hold on. That's how this force relates to this degree of freedom and this degree of freedom. As well as all the other ones too, but those are all zeros, right? It only relates to this one and this one in a non-zero way. And the second row tells us how this force relates to this degree of freedom and this degree of freedom. And the rest of them too, but those are all zeros, right? So that is the stiffness matrix elements in extension. Now, what about in torsion? This is a bit harder, but not all that much harder. So the best way to visualize this is to imagine you're wringing out a towel, full of water. You're wringing it out. You're rotating this in this direction and this in this direction. And kind of imagine how that works. So you're basically applying a torque. You're applying a negative moment, here, a positive moment here, and you're rotating this towel, by some degrees at A and some degrees at B along the x-axis. And again, we can pull out this shear modulus and stress and strain relationship here, and we can solve for the force out of this equation. Basically, the first thing to do is to just take the equation from above. Previously in the presentation, plug in these numbers here for the moment, and then look at the signs. So in this case, we're defining a positive torsion as one that kind of rotates positively around this axis here. So in that case, if you were to hold node A in space, apply this kind of a force, this kind of a moment I should say, that causes a positive rotation about theta at B. So this is a positive sign here. Whereas if you were to apply a positive moment on this side, that would relate into, in order for it to make sense, if you were to fix this one here, apply that positive moment here, this would cause a negative torsion, right? Because you're spinning in the opposite direction on this side, relative, right? So, because this force causes this kind of a reaction here, in order for there to actually be torsion, not just rotation of the part, and so. Yeah, that's how that works. That's why there's a negative sign here and a positive sign there. Now, if you look at the strain, the strains are pretty similar. Again, instead of being length, it's just the total angular change. So instead of it being ux minus ux, it's theta x minus theta x. So theta b minus theta a times r over L. Now, if you look, these both have an r. However, when you plug them in to this expression here, and take the stress over the strain, the r is canceled out. Then you can solve for the moments, pull out the degrees of freedom, and you get this kind of relationship here. This just shows that the moments, mx at A and at B are only related to these two rotations. By what way? By these proportionalities here, and all other stiffness coefficients are 0. So just like before, we can fill out the 4th and the 10th rows and columns and explain how these moments, this moment and this moment, relate to all the degrees of freedom. However, pretty much all those are zeros except for this one and this one, right? Simple enough, right? But now we get on to the hard one, and that's why I left it for last. That's the bending stiffness. Why is it so hard? Why is transverse bending so hard? Well, it's because before, everything was, very simple. You had moments in x causing rotations at x. You had extensions at x being caused by forces at x, in x. In this case, we're all coupled up and screwed around, right? So, if we're bending this beam, this way and this way, like we're bending it concave up, that can be caused in two ways. Well, first off, by a force. We're going to be applying a positive force in this direction. That would cause bending. But also, a moment, right? Moments cause bending around that same axis. So we're looking at moments about the z coupling with forces in the y direction. And so this all gets very, very complicated. And so this, again, has length L. I didn't draw it in, but also it has what's called an area moment of inertia. We'll derive what this is, but just know this is the equation for it. We'll get into what that means later, and we'll actually pull this out of the integration. And so, yeah, that's how this looks. Now, what you have to realize is that for a beam that you're bending, the bottom of the beam gets longer, and the top of the beam gets shorter. So the bottom of the beam is in tension, right? And the bottom of the beam is under, or sorry, the top is under compression, right? Compression. It's getting smaller. And at some point in the middle of the member is what's called the neutral axis. That's where there's no length change. That's this gray line here. And so this x is along the neutral axis as I've drawn it. And so what's important to also realize is that in bending, that extension affects the axial strain. That's, well, I just showed you with, tension here, compression here. That is axial strain, right? If this gets shorter, that's an axial strain component. And so basically, how you can look at that is saying, well, what is the slope? So the slope that you've caused here is actually the amount which you've compressed this system. And if you multiply it by the distance from this neutral axis y, you can actually compute how much you're actually moving in throughout the thickness, right? And so if, let's say this was a 2-inch thick part, at y equals 1, you would have a negative, whatever the slope is, that's your axial displacement here. Whereas if you put in, negative 1, that would be a positive displacement, right? Obviously because this is to the right and this is to the left. So what is strain? Well, I mentioned before that strain was just the change in length over the length. Well, in other words, that's just the derivative. And a lot of these textbooks and teachers will say, oh, well, actually you have to take the partial derivatives and everything. Yeah. But ultimately, that's all going to be zeros. And all that we care about in this system here is the x component, right? So, in this case, the derivative of this with respect to x is just, negative y d squared u dx squared. And what is the stress? Well, stress is just E times the strain. That's just an E out front. Okay? Simple enough. Now, keep that in mind for later. We'll use that later. So stress is just how forces and moments are carried through the element. And so a stress represents an internal moment, in this case about the z-axis. And so if we were to plug this in, right, so the applied moment, we'll call it mz, has to cause this stress, right? Or I mean, it's causing and opposed by the stress, whatever you want to think about. It's related to the stress distribution here. So if you integrate this, so basically a stress is a force over an area, right? So force over area times the displacement for how far you are from the neutral axis here in the y direction, times the area, right? This gives you a force. This gives you a moment arm. So this is your, moment that opposes your applied force. In this case, it's your applied torque, mz. And so you can just plug in this expression here for your stress, integrate, and here is where that moment of inertia comes. We have, we can pull out integral over a of y squared dA, and that's just iz. Other than that, all we have is this, and this is not vary with the area, so we don't really care about that too much. So, but this equation matters a lot. This is the moment equals EI d squared uy dx squared. This is an equation that people have memorized. That's where it comes from. Now, what is shear force? Shear force is a transverse load through an element, and the load carries everywhere. And this is what they call a differential beam element or whatever. They're taking a cut in the part. I'm not going to get into all that right now, but because we're only applying forces at the nodes, right? The shear force that carries through this element, it can't change, right? I mean, if the force here is 15 newtons and the force here is 15 newtons, I mean, the shearing force everywhere is 15 newtons, right? That's what V is everywhere. And because it doesn't change over the length, because we're not applying any forces inside the element, we're not applying any distributed loads here or anything, we're not applying, anything in the middle, we're only applying nodal forces. What's that mean? Well, that means that dV dx is 0. there's no way that v can change over the length x of this member. That's equation number 2. Now equation number 3. So because the shear force naturally accumulates, an internal moment, because it's applied over a distance from a node, we can compute basically that for an incremental distance. So basically v times an incremental distance dx would cause an incremental moment dm. And you can solve for v, that's dm over dx. That's equation number 3. Very simple stuff. And now we'll put those equations together. So equation 1, substitute in mz for m, take the derivative. This is what pops out, right? We're just taking another derivative of this. And the signs, don't worry about the signs. The signs I'll explain later. We'll get into what all that means later in a very clear way. And then we plug in equation, this equation here into equation 2, pull that out. That's EI, the fourth derivative, equals 0. All right. So now the objective here now is to figure out an equation that we can use to capture this. So there's no nice and easy simple equation that we can write that satisfies all of our degrees of freedom. Right? There's no like magical one. We have to come up with one. And so that's the objective here. We have to solve this equation, this differential equation, so that it satisfies a couple of very important boundary conditions at nodes A and nodes B in our part. And so we have to satisfy these 4 degrees of freedom, that is uy and theta z at both nodes. And to go with that expression, that equation, we need, there's 4 of them, we need a cubic function, right? A line can pass through 2 points, a quadratic can pass through 3 points, satisfy 3 conditions, but a cubic is required to satisfy 4 conditions. So we need 4 parameters here, p3, 2, 1, and 0. And we have to solve for the p coefficients such that all of our degrees of freedom are satisfied by in this equation here, right? When we compute this out. Okay. So we're trying to solve basically for this equation here. We're trying to plug in different values for p until we're trying to solve different values of p that satisfy these things for this. Now, one thing that we have to remember is this assumption, and this assumption only holds true for very small rotations, but in general, as long as linear analysis is valid, this assumption holds true. So for small rotations, the theta about the z-axis is, if you look at the exact equation here, that would be just the tangent, right? Tangent of this over this is this angle here, right? So, or inverse tangent, whatever you want to say. And so the small angle approximation basically says, well, basically tangent of the angle is itself, so theta z is approximately equal to the derivative in the x direction. So what does that mean? That means that we can plug in this here and this here, and plug in 0 and L and everything to solve for these p's at this equation, or and we can take the derivative of this, uyx, derivative of that with respect to x dx, that equals the rotations, approximately the rotations. And then we can just take a derivative of this and solve for these two in this equation, and then pull out the p's. So yeah, that's what that is. It's pretty simple. You'll see what I mean in the next couple of slides. So here's the original equation for the displacements in the y direction, and here's for it's the derivative of that for the rotations. So if we were to plug in x equals 0 for node A, right? In solve, this is what the displacement is at 0. It's UA in the y direction, and then the rotation is theta z at node A, right? So these are all 0, 0, 0 cubed, 0 squared, 0, right? We're plugging in 0 for x, and so only p0 and p1 are come out of that, so we can solve for p0 and p1 like that. Now at node B, x equals L, you plug in these values for p0 and p1 like this, And again, you're plugging in the degrees of freedom at L, which is the displacement and the rotation at node B. And then you can do math and you can solve for P3 and P2. Simple enough. Now we can substitute those P's back in the equation. You have this long equation. You pull out the degrees of freedom now. So here we can see how these degrees of freedom are controlling this. And by the way, if you were to plug in, x equals 0 in this equation, what would you get? If you plug in, if you're at node A, and you plug in 0 in this equation, which is x equals 0, what does that mean? Well, that means that this is uy at 0. That is just this, right? And if you plug in L, just this. And you'll see that. If you plug it in, you'll actually see that that comes true. And if you in this equation, if you plug in 0 and L, you'll get this and this. That means that our expressions here work. And these are what's called they're called hermetic shape functions or something. Don't worry about that. It just shows how these values can be interpolated in a cubic way through the element. Right? Cubic because it's cubed. Yeah, so between 0 and L, at 0 and L you have this and this, but between 0 and L you have values that are different, right? And you could plug in, L over 2, and you can see what that would look like if you wanted to. Okay, so these cubic functions can help describe the relevant degrees of freedom and help interpolate between them if necessary. Now, I computed these two extra derivatives here. These just show, this is like the first derivative, but here are the second and third. We'll need these for later. And you can see actually at the third derivative, everything is constant. And, the astute among you will start to see, stiffness matrix terms coming out, but we'll get to that in the next minute or so. Okay, so now back to equation number 1. The sign, again, I'm not sure, it doesn't really matter what the sign is. We'll talk about what the sign has to be in a second. But mz equals ei d squared uy dx squared. At node A, x equals 0, you can plug all that in. Right, all of these, we plug in 0 for x, right? This is d squared uy. We plug that into this equation. You plug in all these zeros. What comes out? Well, these things come out. And you have these basically multipliers for the degrees of freedom. That's how you distribute this moment across the degrees of freedom, is these multipliers here. At node B, it's very similar. The only difference is that you're at x equals L, so you're plugging in L, 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 L. A lot of these things will cancel out. It's always, you can subtract and add these numbers together because they're both over L squared at this point, and you get a similar proportionality between the moment and the degrees of freedom here. Now the sign. People always talk about conventions and concavity and positive, negative, and all this stuff. I don't know any of that stuff. It's too hard for me. All I care about is, does it make sense, right? So ultimately, we want to know that a positive moment causes a positive rotation at that node. So if we're applying a positive moment at node B in the z direction, that causes a positive rotation about z. It has to, right? If we're spinning this way, by golly, this ought to spin this way too. Otherwise, something is severely screwed up. And so basically, that means this sign has to match this sign. And it does. If it didn't match, you'd put a negative sign here. Who needs definitions and concavity and all this garbage and keeping track? Just make it make sense. On the left-hand side, you need the moment at A to be positive and the displacement in a rotation at A to be positive. If not, you put negative sign in front. And here we had to, right? And so that's why this comes out. So I don't keep track of negative signs. It's too hard. Everything messes up. You make mistakes. Don't bother with that stuff. It's a waste of time. So these terms here, I'll show you in a minute. These are the stiffness matrix coefficients in this row. And these are in this row, right? Okay. Equation 3 now, we pull that down. That's just dm dx. So this is actually the third derivative, right? So we plug in, are x equals 0, x equals L in the third derivative equation. By the way, there's no x in that equation, right? It's all constants, so it doesn't matter what you plug in. But yeah, so basically your shear force, V is just your applied forcing, F in the y direction, and then the signs, again, we'll pull out the signs that make sense. So in this case, we want a positive force to move the node up, right? So at node A, these have to both match. So again, there's no negative sign here. But for this one, a positive force at B has to cause a positive displacement at B. And in that case, we need a negative sign. So in this case, this is how the stiffness matrix terms for F in the y direction at node A and node B look. So we can grab these things, these 8 ones and these 8 ones, and throw them in the stiffness matrix, and we're almost done. Almost done. So that was bending about the z-axis, or in the y direction. But now we have to do the other one. We have to do bending about the y-axis. And this one is, I see here, it's basically the same thing, except the right-hand rule betrays us, which it does, and I hate this. And for some reason, no one talks about this. Like I'm looking through these textbooks, and this is like it's like a secret. I don't know. Like no one wants to talk about it. It's like, and for obvious reasons, this is this. It's not obvious, dude. I couldn't figure it out. Okay, so in this case, the only difference is we don't have the z moment of inertia. We have the y one, and so that's, instead of being y squared dA, it's z squared dA, right? And so here's how the right-hand rule betrays us. So before, if you remember, we took this assumption, this small angle assumption, that theta z was approximately equal to dy dx, right? That's that this angle here is approximately equal to the slope, right? And that's just a small angle, like a assumption going on, right? And that's valid for small angles. However, if you now look at the theta in the y direction, this slope and this angle, z-axis is down, dude. So this slope is actually negative dz dx, not positive. And that's where the difference comes. That's the only difference. That's literally the only difference between bending in the y direction and bending in the z direction. It's just this. And so I, very carefully, it took me many hours to go through this, equations and change all these things. I changed all the y's to z's and all the z's to y's and put some negative signs for all the angles, right? So here you can see that the angles became negative, blah, blah, blah. Long story short, derivatives, keep going. Now we're down to the equations, right? So now we're plugging in, 0 and L for x, and node A and node B, and everything here is basically the same exact things before. The only difference is where I put these little asterisks, these things change sign, and these things change sign. So this is the stiffness matrix terms for my at A and my at B. It's almost the same thing. Obviously, these degrees of freedom are now about the z, and these are about the y, as before they were switched around. But everything here is the same. The same numbers, the same derivation. Everything here is identical. We just changed some negative signs in front of the angles. And then for the shear force, again, it's the same thing, except for these terms changed, right? And so take those numbers, plug them all in, and we have this completed 3D frame element stiffness matrix formulation. That's a mouthful. And it's fully symmetric. Everything here is very nicely organized in like a little thatched pattern, very nice. It's like a fence, right? Very grid-like, very cool. And this shows how degrees of freedom are related to applied forces. That's literally all it's doing. That's the takeaway from this video, is just this matrix relates a given force to all the displacements, right? Okay. Now, I hit the maximum number of vertical pixels in this file. So let me open the second file. So that's how you make a single element matrix. The question is, how do you assemble? Remember in the beginning, let me go back. We had that spring example, and to assemble it, all we did was add it together, right? Where is this spring example? Here, we add these together, right? That made sense because there was only 2 degrees of freedom, right? The problem is when you have a lot of degrees of freedom, a lot of nodes, right? The matrix is very big and you have to know where to put these terms in, right? It's not going to be so easy as just lining things up with these equations. You have to be able to do it algorithmically, or else you're going to be there all day basically trying to put these things in. So here's how this matrix breaks down into quadrants. So the upper left 6 by 6 is how forces at node A relate to displacements at node A. Whereas the upper right quadrant is how those same forces cause displacements at node B, right? So these go on this side and these go on this side. And these on the bottom are the same thing, but for these forces. So how do node B forces cause displacements at node A? That's this side. And how do these forces cause displacements at node B? That's this side. Right? If you understand that, everything else is so simple. I mean, all you're doing, imagine that we had like a bunch of other degrees of freedom in here, a bunch of other ones that we don't care about. Say we had a node that was in the middle here that we didn't care about. That would just mean that we had a bunch of zeros, along this direction and this direction. We actually would have 6 rows and columns of zeros in between all of this. I'll explain that in more detail right now. So let's say you had this structure here with 4 elements, 1, 2, 3, and 4, and 4 nodes, 1, 2, 3, and 4. Element 1 looks like this. Element 1, so here's basically a bunch of, I broke this all down into each degree of freedom here. So there's 6 nodes, or sorry, what am I saying? There's 4 nodes, and there's 6 degrees of freedom. And so each one of these things is, 6 by 1, because there's 6 degrees of freedom per node. So this total length is 6 times n equals 4. So it's, what is 6 times 4? Open your calculators. And same thing on the right here, 6 by 1s, and there's 4 of them, 6 times 4, that's how many elements there are here. And now, so element 1 connects node 1 and node 4. So basically that means that all we care about is what's in the 1, 1 slot, the 1, 4 slot, the 4, 1 slot, and the 4, 4 slot. So we take the elements in this matrix, this little guy, or I should say, hold on, this little guy, we saw it down horizontally here and vertically here. We snag this corner, this corner, this corner, this corner, all separately, and we throw them in here. Bam, 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 bam. Then element number 2 comes along. Element 2 is nodes 1 and nodes 2. So in that case, we're putting those 4 quadrants here, 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 and here. And you'll see that for these ones, we just filled in the zeros, but here we actually added it together. So we've added the stiffness basically has to be distributed. The force is distributed across both elements. If this element is made of reinforced titanium, this one's rubber, obviously more of the force is going to be invested in deforming this than this if they have to displace in the same degree of freedom. So you have to add them together, right? Then element 3, we're plugging in this one, this one, this one, and this one. And then element 4, we're plugging in this one, this one, this one, and this one. See how that works? We just slotted in the degrees of freedom into the corresponding rows and columns based off the nodes that were involved. So if we needed nodes 1 and 4, we slotted it into, nodes 1 and 4. We put it into row 1 and 4, column 1 and 4, right? So it's extremely simple. I mean, this is, first grade SpongeBob. Okay, now, there's one more thing about this matrix that I didn't mention. It's that when we're applying forces and stuff and looking at displacements, we don't want them to be in the local frame. And also, if you want this to make sense, these all have to be in the same frame. You can't be adding, if one of these elements has x in this direction, like element 1 does, and one is in this direction, like this one does, this is all screwed up. I mean, x has to line up. You can't add the u1 degree of freedom unless it matches, right? If u1 is this way for this element, it has to be this way for this element. It has to match up, or you can't just add like this. And you could go and you say, oh, well, this is y and y is x and everything, and do this all kind of intuitively. Or you can make just some simple math, right? So, and this gets really hard once you have like 3D rotations and stuff. It's very difficult to keep track of all these things without having a nice transformation matrix like this. So we have to go from the global system to the local system. And so we ultimately want to have this equation here. This is our goal of the video, is having all of the forces in a global frame equal some global stiffness matrix, which we don't know. That's something that we don't know right now. And we want to compute these degrees of freedom in the global frame. And so we don't have this K, G, but we do have the local ones. We do have the forces locally, right? Or at least we have this. We have the stiffness matrix locally. That's what we just defined for the past half hour, was this, this crap. So we have to be able to figure out how this works. So what we're doing is we're defining this matrix T, which relates from the global to the local, both for displacements and for rotations. What am I saying? Both for displacements and for forces. I'm getting loopy right now. This is too long of a video. So we can plug in these two things here, TU and TF, into this equation here. And kind of we can pull out that the global stiffness matrix is just the transformation matrix inverse times the local stiffness matrix times, again, the transformation matrix. So that's all we're going to do. We're just going to compute this, compute a T matrix, and then pre-multiply this by the inverse of T, and then post-multiply it by T, and then slot it in this matrix like this, and we're done. That's how this whole system works out. So this is how the transformation matrix looks. It's mostly zeros. All we're doing is we have these 3x3 blocks that we're trying to create, and these 3x3 blocks basically relate the local, or I should say the global x, y, and z to the local x, y, and z, right? And so people talk about like, oh, direction cosines and quaternions and all this stuff, but those don't make any sense and they're make-believe. So we're going to do it the old-fashioned way with dot products, like God intended. And so each of these little 3x3s is the same, and I'm going to call them gamma. I think this is gamma, right? And the way that works is we just have to be able to quantify the axes in the other system. So you can think about this in a couple of different ways, but I think the easiest way is to say that this row here is the local x-axis, call it this one, the one aligned with the beam element from node A to node B, that we're going to quantify that in the global x, global y, and the global z-axis, aka this is a unit vector, in the x-axis direction. It's a unit vector in the global system for the x-axis. So the first row is very easy. That's just, like I said before, the unit vector from node A to node B, and so you compute the length. By the way, you need the length for everything else in this. This matrix has length everywhere. You kind of need this anyway. So we'll already have this, but you will need this for this as well. And what is the unit vector? It's basically just the node B minus node A over L, both for x, y, and z. So this is the XL unit vector in the global system. And now you have to compute the y and the z unit vectors. And this is where you get to kind of pick what you want to happen. Now, the question is, how do you define the local y and the z-axis? Because if this is your x-axis, this light blue one here, is y going to be up? And if y is up, I guess z is to the right. But what about, can y be this way, or is y this way, and then is z this way? But what's what? I mean, what are you going to do? Like, you have to pick. And so the way that you pick is arbitrary. But there's a couple options. And again, it matters, right? It matters which way is y and z, because y has to align. I mean, usually, like for an I-beam, right? This is an I-beam. This structure is much stiffer in this direction, bending in this direction, than it is bending in this direction. That's just a geometric property because the material is further from the neutral axis. And so the way boomers do it, and we've seen these textbooks, is they define a point. Well, not everybody, but what I've seen a lot is that they define a reference node somewhere in the local xy plane. Xy plane is basically this plane here. They define a point, define a point in this plane, and they basically say, okay, well, this vector v goes from node A to that point, and then if you take the cross product of vector v with the x-axis, or I should say with x, sorry, you take the cross product with x with the v, you get the z-axis. right? That's true, right? If you use the right-hand rule on this, you put your index finger here, or your middle finger this way. This would be where your thumb would point, right? So that's the right-hand rule. So this is Z local. So Z local we've defined by this reference node C. And then what you do is for the Y local is you take the Z and the X, and you take the cross product of Z with X, and you get Y. And in this case, if you cross Z with X, your Y is in this direction. Right? And that's fine and dandy, but the problem is it's so much work to do this. I mean, you have to think about in general. I mean, this is going to be in 3D space. You're going to have X, Y, Z for this. You're going to have X, Y, Z for this. You're going to have to figure out where this node is in space, somewhere on this plane. It could be rotated some off angle. It's really hard a lot of the time, and it's much easier to come up with just the vector by itself. And that's what I'm going to do here. So we're just going to find a vector, and this is easier because a lot of the time, this is already going to be in an axis, right? There's going to always be an axis in this direction. Like, I think I have to draw something. Let's say you had a beam that was like this, and this was your X direction and Y direction, and Z was out of the plane. Well, this was an I-beam. It doesn't matter because if you put the V equals, 0, 1, 0, the positive Y-axis, that would also prescribe vector V. You don't need to put a point there and calculate all this stuff. You could just put in 0, 1, 0, and this would all fall out properly. Okay, remember you have to normalize these things though. You can't just use regular vectors. It has to be a unit vector, and that's very important. And I'll talk about why right now. That's because a cool bug fact: because the rows of gamma are perpendicular and unit length, both gamma and that T matrix are both orthonormal, which means the inverse is the transpose. So I mentioned before that we had to take the inverse of this matrix. Inverse of T times K times T. Well, in reality, this is just T transpose, which makes this a heck of a lot easier to evaluate, especially because you have to do this for every single element. So T transpose KT is what is the global matrix, or I should say the global reference frame of the element matrix. Does that make sense? It's the set of matrix in the global frame. Okay. So yeah, that's all that. Okay, last thing. This is really the last thing we're talking about today. That's boundary conditions. So there's two kinds of boundary conditions. You can specify a force or a moment, or you can specify a displacement, right? So going back to, let me see, that bike, you can apply a force, or you can say, hey, I'm going to turn the handlebar, this many degrees, or this many inches, or we're going to push the seat down this much, or we're going to, whatever you want. You can apply actual degrees of freedom, or you can apply, like for example, this degree of freedom here is set to 0. Both, the displacements are all zeros, and the rotations are all zeros. So you have 6 degrees of freedom that are all 0 at this node here, right? So there's two things that you can do. I mean, forces and displacements, and they're both pretty straightforward. So to apply a force, all you do is you put in the value in the force matrix. Okay, it's a huge breakthrough there, right? I mean, it's all zeros to begin with, and you just plug in the forces that you're applying into the proper slots. So if you're applying a force at degree of freedom number 3, it would go here. If you're applying a moment at degree of freedom number, what is this, 5, it would go here. Okay, simple stuff. Now for displacements, it gets a little bit more challenging. So I made some examples here, right? So this is an example where we had, this is not a frame element, this is only a 6x6 just to show, but let's say we had row 3 and row 5 are going to be applied forces, and let's say rows 1, 2, 4, and 6 are going to be specified displacements. So the degree of freedom U1 is U bar, U2 is U2 bar, U4 is, theta 4 is theta 4 bar, theta 6 is theta 6 bar, all that stuff. So to kind of make this work, what you do is think about how this sets up in the equation, right? So this is your source matrix. You have to make this make sense, right? So row 1, U1 bar has to equal to U1. I mean, this stiffness term, K11, has to be 0. Right? and U2, that has to be 1. It has to be 1, basically. This has to be 1, this has to be 1, because you have to make the displacements match up with the prescriptions. So we're prescribing it to be U1 bar. That, U1 has to equal U1 bar, right? Same with U2 has to equal U2 bar, all this stuff. Now, for the force rows, where we have these forces being applied, so we had a bunch of zeros here, basically. This was a 0, this was a 0, all these zeros. We don't care about the other degrees of freedom. It's all we care about in this first row is defining U1. Second row is defining U2. Fourth row is defining theta 4. Sixth row is defining theta 6. Right? But at rows 3 and rows 5, we're not just setting these values. We have to actually compute these things. I mean, that's the whole point of this method, is that we're computing these values. And so you have these full sets of degrees of freedom here. However, the difference being that you can actually kind of secretly plug in the prescribed degrees of freedom, because remember, this column was U1, this column is U2, this column is U3, this column is theta 4, theta 5, theta 6. You can, because you're prescribing U1 to be U bar at 1, you can just plug in U bar. You don't have to have U1 there, just have a U bar. Have a value there. Same thing with U2 and theta 4 and theta 6. Plug in the bar versions of these values. And then, because we always want to have the knowns on the left-hand side and the unknowns on the right-hand side, here's how that matrix would take shape. So you can see, this is like the takeaway. Wherever we had a prescribed degree of freedom, surface matrix is just 1 and a bunch of zeros. So actually what you do to this is that you basically make this matrix in the beginning just without any boundary conditions, and then you say, okay, well, we're prescribing U1. What are we prescribing? Well, we're prescribing U1 to be U1 bar. And then you say, okay, well, let's get rid of this. Let's get rid of this. These are all going to be non-zero. They're going to be, EA over L, GJ over L. All this stuff's going to be in here. You say, screw all that garbage. Make them all zeros. Make these all zeros. So this means these are all zeros, and these are all zeros. And this is not, 12 EI L cubed, whatever. This is just 1. Similarly, for this second row, you set this to be 1, and then everything else to be zeros in that row and column. And then you plug in U2 bar here. Then for, same with theta 4, you make all these zeros, and this is 1. And then theta 6, again, these are all zeros, and this is 1. And then for the forces, we have to bring all this stuff, this one, and this one, and this one, and this one, and this one, to the force side, because they're known values. They're not unknowns anymore. So here's how you do it. You subtract them all to this side, and you put them over here. Now, this gets a heck of a lot easier when you're prescribing a 0. When you go back to this and you say, oh, well, these are all going to be zeros here, and all zeros here, and all zeros here, and all zeros here, you don't care what the numbers are anymore. This is 0, right? This is a 0. This is a 0. This is a 0. And guess what? All of these are zeros. Boom, 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 boom. And at that point, you get something super, super easy to evaluate. You have just, 0, 0, F, 0, M, 0. And then this, this is super simple to evaluate, right? So it gets very, very easy. So boundary conditions are extremely easy to implement. And here's how that looks. If you want to just reduce that, you don't have to do this, but some people like to do this. You kind of can take out all the known degrees of freedom on different equations set here. So U1 is U1 bar, U2, U2 bar, theta 4, theta 6. They're all in their own set of equations. And then you pull out all these garbage rows and columns that you don't need anymore. All right, boom, 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 and boom. As well as on this side. What am I doing? And then this side as well. Boom, 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 boom. Get rid of all those garbage things, and you keep what's important, and you can solve for this. So here is the summary of the process. Okay. First thing you do is you initialize. First of all, you count the number of nodes you have and degrees of freedom and all that, and you initialize these vectors F, U, and matrix K. So this is basically just a matrix that's 6n by 6n. This is 6n by 1, 6n by 1. Okay. Then you loop through all the elements, and you compute their local elements to this matrix. That is this, right? And this is purely geometric and material, right? And there's also the vector v we talked about, right? You have to know that as well. But you're computing this local element stiffness matrix. It's a very straightforward thing to do. Right? Literally just plugging in numbers in this 12 by 12. Then what you do is you convert that local stiffness matrix into the global frame. So you take this 12 by 12 and you pre-multiply it by this t transpose, post-multiply by regular t, and you get this. So it's some weird version of this. It's going to look a little bit different. There's going to be different spots. But yeah, it's going to be basically this, but just rotated a little bit differently. Then you cut that in half. You saw this down here, and you drop the quadrants of this transformed matrix, this KG, into the full matrix, right? So you slot those in just like we did up here. You put those in like this, all those things. Then what you do is you apply the boundary conditions. That's this stuff here. Again, it's super easy. You just literally crossing out rows and columns of your matrix that you just spent so long to make. You just cross out all this garbage. You put ones and zeros everywhere. And then you solve the system. You take K inverse of your reduced system or this system, whatever you want. This is actually easier to do most of the time. You don't have to work with all this, getting rid of these rows and columns. Yeah, you just solve the system and you're done. Now you have U and you have what you need. And this point is where you say, well, what do I need now? Do I just care about how much the bike is going to deflect when a fat guy sits on the seat? Do I care like, oh, well, it's 200 pounds, the bike's going to sink by 1 inch, man, all these shocks and stuff? Or do I care about the strains? Now, if you care about the strains and stuff, you have to post process. And we have functions for this. Remember, the strain, the tensile strain, it's the axial strain, just due to tension alone is, remember, it's this. It's the, if you had your element like this, the U at B minus the U at A, that's the length change divided by L. So you can compute the strain just by taking these values, right? Just take these two values, subtract them, divide it by L, which you know, and then multiply it by E. You get the stress if you want. I mean, if you care about the stress or the strain, you can compute both. Torsion is the same thing. You plug in the value of stability degrees of freedom that you solved for just now very carefully, and you know R and L, you know G. You can solve for both the shear strain and the shear stress, if that matters to you, right? And then axial stress. I mean, remember, axial stress is not just tension, but you also have to add in the bending components. And so you have all this stuff. I mean, you have these functions. You have these shape functions that you can evaluate anywhere along the part. You want to plug in x equals L over 2. You want to plug in x equals L over 3, L over 4. You can plug in anything you want in these shape functions, and you can compute these derivatives and plug into these equations and get the stress and the strain very, very easily, right? And remember, you have to do both y and the z, right? So it's all very simple stuff. I'm not going to get into that. That's for you to learn on your own. But it's very easy to take these u's and compute relevant quantities of interest that you might need. All right, last thing I want to talk about really quickly is a full example. And so I've got this ladder here. And basically this ladder, I'm just showing the overall process. And we're going to talk about what goes into coding this up. So you have a ladder, and it's made from, let's say, wood that's 1.5 by 3.5 inches for these rails on the top, on the left and on the right. And there's a 1 inch diameter rungs. And everything here is made from pine wood. And these are the approximate properties for pine wood that we're assuming. It's isotropic. We're going to assume that, not in reality, but we're going to assume that it's isotropic just for this quick analysis. So we're applying some forces. We have some guy here on the top, 200 pounds, and we have some guy here pushing the ladder in just to hold it steady. He's helping out. He's being a nice friend. And the ladder has some dimensions. It's 2 feet wide. Each of these rungs is 1 foot up, except for the top rung. That's 1 foot from the top of the bar there. So yeah, very straightforward structure here. One cool thing though, I put it at a slight angle here so it kind of can take into account some other axes. And the bottom two legs here are fixed, and the top is up against the wall. And so we are constraining these degrees of freedom. This one is fixed in place, but this one can just not move in this direction. Obviously, it's against the wall. It can still move in this direction, right? But it can't move in this direction. Okay. that's all of that. Now, a couple questions to answer. So, what are the different cross sections that we have? We have a cylindrical cross section and a rectangular one, and so we can compute, these polar moment of inertias and the area moment of inertias based off the expressions that we had come up with previously, because we need these for our matrix, right? These are values that we care about dearly for going into here. We need to know IY, we need to know IZ, we need to know, L obviously, A, and all these things, and J. These all have to be known. You have to compute all those things. And so that's the process here. Integrate all that stuff. I'm not going to go through all this. There's actually, textbooks. There's reference sheets and textbooks on this topic. You can just look up what is the moment of inertia for a circle. What is the moment of inertia for a rectangle, and you'll get these things. One cool takeaway though is that that I didn't really know until recently is that I didn't really think about this, but the polar moment of inertia is just the y and the z area moment of inertia is added together. Very cool. I didn't realize that, but that's always the case. Interesting. And also, we're going to be using the global vector 0, 1, 0 as our vector v. Vector v being, here we go again. Let's scroll up. Vector v being, this vector here, because that will basically be in the plane, in the xy plane for all of our cross sections. This vector here. Oops, let me draw a line. This vector here will be in the cross section in the xy plane locally for all of our elements here, because this element, this is the the y-axis for the element as I drew here, and this can be in that plane. This is not perpendicular to that plane. So yeah, that's all that. Now comes to the question is, what different kinds of elements do we have besides just the cross sections? Well, we have elements that are cylinders, and for cylinder elements we have elements that are 2 feet long or 24 inches long. So that would be all of these elements here. Where's my pen? So this element, this element, this element, element. Those are all 2 foot wide elements. And you can see I labeled all the nodes. The nodes are labeled 1 through 19. I put one node here where the guy is standing, because you have to put a node there. You can't apply a force without having a node. So I put a node where the guy is standing. And the guy that's pushing over here at node 5, I put a node there. Node 5? Yeah, node 5. Just because he's pushing there, we have to have a node there. And so nodes 1 through 19, and then elements, 1, 2, 3, 4, all the way down, and then down the rungs, and then down the right side, all the way to 24. And so, as I said before, in terms of cylinder elements, we have 6 of them that are 1, 2, 3, 4, 5, 6 of them that are 2 foot long. We have 2 that are 12 inches long, that's 9 and 10. And we have a bunch of elements that are rectangular and 1 foot long, that's all of these elements. And all of these elements. And then we have elements that are rectangular but half a foot long, that's number 1 and 17. Okay? And so if you wanted to, you can compute the stiffness matrix just manually. You could just go over here, okay, well, I'll plug in these values, L is 6 inches for this one and 24 for this one, and then the I's and the E's and stuff. Well, the E's are all the same, they're all from wood, and the G's are all the same, from wood, and the I's and the J's, they come from this, and you could do it all manually, but it's easier just to code it up. And so now what the boundary conditions, what are they? So in this case, what are we applying? So FZ, at node 5, we're applying the guy pushing, right? He's pushing with 100 pounds, and that is in the negative z direction, as I've drawn it here. So 100 pounds negative z, right? Then we have 200 pounds in the negative y at node 10. That's node 10. That's this way. So 200 pounds downwards, correct? Y is up. 200 pounds is negative. Then we have at node 9 and 19, it's fixed. So these were all fixed, remember? Fixed in space. And then nodes 1 and 11 are fixed in that they can't move in the z direction. So remember, z direction is this way. So this degree of freedom was set to 0 for nodes, nodes 1 and 11. They can't move in the z direction. So uz 0 for both nodes 1 and 11. And now we're done. You just go on the computer and you program this up. So how does this work? Well, let's take a look. So I have some functions here. Let me zoom in. I have a, this is the, the overall function. Hold on. So yeah, here's my ladder function. Basically at the top of this, I'm defining the nodes. So this is the x, y, and z location of every node in this ladder, right? X, y, and z location of every node. So, this is node 1, node 2, 3, 4, 5, 6. And actually, I parameterize the angle out. So you could theoretically change the angle or whatever. What is this garbage? Oh, I pasted something in. Oops. Okay, so this is all the nodes. There's, what, 19 nodes, I think. And then here are the elements. So the elements is just me saying, okay, well, element 1, that's the first row, has node 1 and node 2. And the element type is something else. I'll get to that later. So basically we have 24 elements, and the elements include all these nodes. So element 24 has node 18 and 19. Let me just go prove to you that's the case. 24, 18, and 19. And the element type is, was it type 2? Yeah. So here's the element types. So what this is, just encodes all the information in a single row of a matrix. So we're encoding material properties E and G, and then geometric properties A, IY, IZ, J, and then the vector V as well in one row of this matrix. And so we have one row for the, you can see the circular ones have a pi in them, and the rectangular ones don't have a pi. And so yeah, this is just telling you, this 2 means it's a cylinder, it means it's a rectangle, and this 1 means it's a cylinder element. That's all that means. That's the definitions. Now at that point, what you do is you, again, like I said before, the first step of this was to initialize these vectors f and u in matrix K. So all we're doing is I'm computing the number of degrees of freedom. I'm multiplying this. This is just 6 times the number of nodes. Number of elements is just number of elements in this vector here, in this matrix here, number of rows. And then we're initializing f and k. We don't care about initializing u because u we're solving for, and so we don't have to initialize that one. We're initializing, an 6n by 1 f vector and a 6n by 6n Stiffness matrix, and then we're assembling the local Stiffness matrices into a global one. And so for that, we have to look at this function here, frame element matrix transformed. And we're just looping through all the elements, and we're calling this. So what does that do? This is just a function that outputs the TKT thing, the T transpose times K. Where is that? This one. And all it does is it literally it takes in the element, it computes, it grabs those global variables for the nodes and everything. I don't want to pass in these things. That's a lot of stuff to be passing around. I'll just take a global value, and we're taking nodes A, node B, the element type, all that. Computing the L, we're pulling out the E's and the G's and all these from the element type row, right? And then we just initialize the local matrix 12 by 12. We plug in all these values. These are all the non-zero terms. This is all this stuff. Very simply, plug it all in. It's a lot of stuff, but you just make sure it's all correct. Then we're computing these local unit vectors in the global frame. That's this, right? That's the gamma matrix. Yeah. And we're computing T. And then we're just solving for T transpose KT, and then outputting that as the output of this function. So yeah, at that point, all we're doing is, but this time we're breaking it up. This is where we're sawing it in half in both directions, and we're slotting it in. That's this part up here. Come on, yeah, this part here. We're breaking up the 12 by 12 into 6 by 6s and putting it where it needs to go. That's what this set is doing here. And then now we have the boundary conditions. So we're just here, I'm applying this is at the proper degree of freedom, because don't worry about this math, you can figure it out yourself. This just means that we're applying a negative 100 pounds in the proper row of the F matrix, and then we're applying 200 pounds negative in the proper row of the F vector here, for this is the guy standing. And then here we're applying all the 0 degree of freedom. So these are all the degrees of freedom. Don't worry about what all these things mean. It just means that this is a list of all the degrees of freedom that we're fixing to be 0. So that is all of these ones, and these ones, all fixed to 0. And then what this for loop does here is it loops through all these degrees of freedom that we set to 0, and it just does what we did before. It sets all the rows and columns to match up with this. So everything, here is 0, everything here is 0, everything here is 1. That's all it's doing in this for loop, right? Sets the the rows and the columns to be zeros, and then that diagonal term to be 1. And then last thing, we just solve the system. Very simple, one line to solve for the degrees of freedom. And then I have a function here that prints out the degrees of freedom very nicely. Don't worry about that. It just helps us see what's going on. And then I have a function here that draws the mesh here. So what this does is it takes in nodes and elements, U, and this is a magnification factor. We'll use that later. Basically, it just plots the undeformed mesh, and then it plots the deformed mesh. You can see it applies, it adds the displacements to the element, node locations as well. And also it has this magnification factor, so if you want, you can multiply the displacements by a factor. If you can't see them very well with a factor of 1, you could put in a factor of 10, and you can see a 10x magnification of what the degrees of freedom are doing. Okay. So if I run this, octave ladder.m. So let me just show this side first. Actually, hold on, let me show this side first. We'll show this side first. So this is basically the ladder. So this is the ladder. You can see here is where that guy is pushing, and here's where the guy is standing. And you can see there's almost no effect, right? There's almost no effect of this guy standing here and pushing here. And actually, this would be symmetric if the guy wasn't pushing, right? But you can see how this guy's bending the top rung a little bit with his weight. This guy is kind of bending the left hand 2x4 a little bit with his force, and all that. So that's what's happening with the degrees of freedom that you can see. But I want to show you this. So here are the nodes and the degrees of freedom plotted out. So if you remember, we said that nodes 9 and node 19 were having 0 degrees of freedom. And so you can see, where is it, that prescription holds true, right? Nodes 9 and nodes 19, everything in degree of freedom is set to 0.00000, right? That's all zeros. And then you can see at node 11, the z component and node 1, the z component, are both set to 0. That is this. Node 1 is 0, and node 11 at z is 0. So that's all that. And then, I guess if you really cared, you can kind of look at, was it node 5 and node 10? So at node 5, we're applying a force in the y direction, no, a z direction, right? Yeah, z direction. You can see that's the most z deformation that you have is at that node. And then at node, what was it? Node 10, we're applying a y force. You can see that this is the y displacement at node 10. That's a pretty massive deflection. That's a 0.4 inches downwards. But now let me actually go back into that ladder function, and let's change that factor from a 1 to a 50, just to get a better idea of what the displacement's actually doing. So I can rerun all this, pull this open, and now you start to see that stuff is kind of looking a little bit wonky, right? So the guy on the left, the guy who's pushing the ladder into the wall, he's not really helping out anymore if you magnify the factor by 50. Let me go back and let me turn that off. Let me turn off his force. So I go into the ladder function. I can turn off that guy. That guy, you've served your purpose. Let's make you go away. Without that guy, you can see it's much more symmetric, and you can kind of see this very cool deformation going on. So again, you can see the top of the ladder. It's constrained that it can't move into the wall, right? But the angle can change, right? The angle can change. It's kind of gotten a little bit more of an acute angle there. The bottom ones, the angle is fixed, so that can't move, but the top ones can. And you can see with this linear analysis, because we took one time step and we multiplied it by a factor of like 50, you can see kind of it's a little bit wonky here, right? The guy is stepping down. Why is this this location moving out in the z direction like this? Well, that's because it's a combination of a rotation and a displacement. Like this node here is rotating, right? What those are nodes 1 and what are those nodes? that was node 1 and 11. So node 1 and 11, what is the displacement there? Let me close this really quick. The rotation about the z-axis, that is, yeah, here you can see it's non-zero. It's rotated by this many radians about the z-axis for node 1 and node 11. So yeah, that's all that. So now if I just run this again really quick to show you, if you took a time step and you were to iterate this over time, this would not be coming down at an angle. It would reevaluate itself to be coming right down vertically. That's what I'm trying to say. And then lastly, a question that you might have is like, why is this rung snapped in half, man? This rung should not be snapped in half. This should be a nice, if I go back in the function and I change this to back to a 1, it looks better, but even still there's a problem. It's a linear assumption, right? We're assuming that it's a line. But in reality, here's the thing. In reality, we're not, I'm just plotting the nodes and a line between them. In reality, what you have is you have a curve, right? And that curve is actually defined by those shape functions that I mentioned before in the bending direction. And so you could actually go through and you could plug in an exact, function that, matches the slopes and matches everything at all these points using the shape functions that we talked about, and plot all these things. But ultimately, for this simple, example, I didn't want to do that. But yeah, that's how this works. So you can see just how straightforward it is to implement this. It's super simple. This video was an hour and a half long, and we covered literally everything from the basics of structural mechanics all the way to the full implementation of finite element analysis. And yeah, it's hard to do that, man. I mean, it's hard to do that, but ultimately it's not a challenge to implement this. Everything is very straightforward. And if you don't care about the math behind it, I mean, programming this up, literally, what was it? It's like 200 lines of MATLAB code, and half of that is just stupid node definitions, element definitions, right? It's just these, just this stuff up here. This is half of the function. It's just all this. The meat of it is this, and this, and this, and then you're done. It's like 25 lines, if that. So it's extremely simple. There's no reason to go through these extremely high fidelity software if you don't need to. A lot of these problems you can just solve just with very easy code. And so I don't want that to get away from us, as a society, as humanity. This stuff is very easy to implement. We shouldn't let these software packages devour us and drain our wallets. So anyway, I hope you enjoyed the video. If you do, leave a nice comment, and those really motivate me to make more videos. So anyway, thanks. Have a nice day.